Page 97, Lesson 2.3 is on equivalent ratios or proportional relationships. So if you look on page 97, weight is a measure of the force affected by gravity. The moon's gravity is less than the Earth's gravity, so objects weigh less on the moon than on Earth. Using the information provided, how much do you think a cat will weigh on the moon? Explain your reasoning. So you can look at the information here. So they've got a rabbit and they've got a dog, a German Shepherd, and they're showing their weights on the Earth and their weights on the moon. So since there is more gravity here than on the moon, the weights are higher on Earth than they are on the moon. So one thing we could do, we could compare the weight on the Earth to the weight on the moon. Since the weight on Earth is more, I'm going to put that on the top. So it's 4.5 pounds for 0.75 pounds on the moon. And kind of like we did in the last section, it might be nice to know how much it weighs for every 1 pound on the moon. So if we divide both of these by 0.75, 4.5 divided by 0.75 is 6, which means, for this rabbit anyway, 6 pounds on Earth for every 1 pound on the moon. And we can see for the German Shepherd, similar idea. So 90 pounds on Earth for 15 pounds on the moon. If we divide both of those by 15, that would be 6 over 1 as well. So 6 pounds on the Earth for 1 pound on the moon. So once we get to that point, we could try to think about how heavy a cat might be. And there's a little variances here. Let's say the cat maybe weighs 9 pounds. So if we look at this, this is on Earth and the moon. So if it was 6 pounds on Earth for 1 pound on the moon, and we're saying if it weighs 9 pounds, you might look at that and you might say, well, going from 6 to 9, I'm not really sure what that pattern is. And we could get it easy enough with a calculator. Even if we didn't have a calculator, though, remember, patterns can be going across or up and down, multiplying or dividing. So we could also go this direction. Going from 6 to 1, that would be dividing by 6. So our denominator is 6 times smaller than the numerator. So then you could do 9 divided by 6, which is kind of where we were at earlier. But anyway, so that's 1 3/6 or 1.5. So it'd be 1.5 pounds, 1.5 pounds on the moon if it weighed 9 pounds on the Earth. A simpler example, just to make it work with the 6, is we could say if it was 12 pounds on the Earth, that would be a definite pattern. Going from 6 to 12 would be multiplying by 2, so that would be 2 pounds on the moon. So in general then, 2 ways that we could say that. We could say the weights are 6 times more on Earth, or we could say the weights are 1/6 on the moon compared to on Earth. Example 1 talks about recognizing proportional relationships. So on Sarah's favorite mobile game, she is awarded game lives when she finds gold coins. How is the number of game lives awarded related to the number of gold coins found? And explain. So you can see on the first picture here, she's got 9 game lives for 3 coins. Here she has 6 game lives for 2 coins. And over here she has 15 game lives for 5 coins. So if we take that information, here's one way of looking at it. We can take that information, we could write those as fractions, ratios. Okay, ratios as fractions. And then one thing we could do at that point is we could try to reduce these. So 3/9, if we reduce both of those by 3, that reduces to 1/3. 2/6 reduces to 1/3. 5/15 reduces to 1/3. So in the numerator was our game lives. So what that means then is for 1 game life would be, for 1 coin is 3 game lives. Another way of looking at it, what the book did is they made this ratio table to see whether the ratios were equivalent to each other. And again, there it is that you can see those are all reduced down to 1/3. So this brings us to the idea of proportional relationships. So there's a proportional relationship if all the ratios that relate to the quantities are equivalent. So if the ratios are equivalent, in other words, if they all reduce to the same thing, or if they all divide out to the same thing, then they're proportional. So for example, if we have, like on this problem, if we have 1/3 and 2/6, that would be an example of a proportional relationship. So on this example, like we mentioned, all these ratios are equivalent to 1/3, and so this is proportional. Kind of another example, a real life example that goes along with this, we could think about if we were making a recipe, using a recipe to make something. If you do a double batch of your ingredients, those should be proportional to what the original batch was. Everything in a double batch is going to be twice as much of what the original batch was. On the Try It, Miles records the time it takes to download a variety of file types. How is the download time related to the file size? And explain. So if we look at the table over here, for a document, the file size is 1.25 megabytes and the download time is 25 seconds. So they have it set up, they want the download time divided by the file size. So watch that. Make sure you're putting that in the right order here. So download time divided by the file size. So download times 25, file size is 1.25, and if you divide that out, they're saying it's equal to 20. We'll trust them on that. The song, 72 seconds for 3.6 megabytes. So 72 divided by 3.6, again they're saying is equal to 20. And the video is 125 seconds for 6.25 megabytes. So that one they've already got set up the ratio 125 over 6.25, and if you divide that out you will get 20. All of these 20s you could put as 20 over 1 if you wanted to. These are like unit rates like we've talked about previously, and what that means is 20 seconds for every 1 megabyte, or 20 seconds per megabyte. Usually, a lot of cases, we have time in the denominator. We would see how many megabytes per second that these are downloading, but they've already got it set up for us this way, so we'll just go with it. If you did it the other way, the answer would be the reciprocal of this. So instead of 20 over 1, it would be 1/20th. So it'd be 1/20th of a megabyte per second. So if we go back over to the side here, we can see the ratios for each pair of data are, so they're the same. Another word for that we could say are equivalent. So the download time and the file size are, so if the ratios are equivalent, we said that means they are proportional, or there's a proportional relationship, means they're proportional. So the convince me, it says, how can you show two quantities have a proportional relationship? And that would be by showing that their ratios are equivalent. Example 2, is the relationship between the area and the side length of the squares proportional? And explain your reasoning. So if you look at this, we've talked about it before. Area of a rectangle or area of a square is length times width. So for this first square, side length is 2. We would do 2 times 2, so that area is 4. For the second square, we would do 3 times 3, which is 9. And the last square, we would do 4 times 4, which is 16. So you can see these numbers in the table, the side length and the area. So they're setting this up as the area over the side length. So they've got the 4 over 2, and that's equivalent to 2 over 1. If we reduce that, 9 over 3, 9 divided by 3 reduces to 3 over 1, and 16 over 4, 16 over 4 reduces to 4 over 1. So you can see these are not equivalent, and that means that these are not proportional. So like the book shows here, those ratios are not equivalent, and so they are not proportional. And basically, once we found out the second one was different than the first one, that would really be enough at that point for us to tell that they're not going to be proportional. But at that point, we may as well check the last one just to verify. Maybe if you get 2 of them that match and the third one doesn't match, then you might just double check to make sure you didn't make a mistake on the other one. So on the try it, the table at the right shows information about regular hexagons. Is the relationship between the perimeter and the side length of hexagons proportional? And explain. So hexagon has 6 sides. A regular hexagon means all the sides are the same length. So we have 6 sides, they're all the same length. So if the side length was 2, to find the perimeter, the distance around it, we could just take 2 times 6, which is 12. If the side length was 3, we could take 3 times 6, which is 18. And then we're going to check to see whether these ratios are proportional. So kind of like they did on the previous example, they've got this labeled as X and Y. And so we're just going to follow their example. We're going to put Y over X, which works out pretty well here again because Y is bigger than X. So we have 12 over 2. 12 divided by 2 is 6. Or we could just reduce those and then say that would be 6 over 1. For our other one, we would have 18 over 3. And if you reduce both of those by 3, that would be 6 over 1 as well. So the question is whether the relationship is proportional. Since both of those ratios are the same, they both are 6/1, then we could say yes, it is proportional because the ratios all are equivalent to 6/1. Now, if you did it the other way, if you did the x over the y, then it would be 1/6 instead of 6/1, but they would both be equivalent. And so either way, that's showing that it's proportional. Example 3 talks about a proportion. So proportion is an equation that represents equal ratios. So we're going to look at this. There's a table that shows how many times a hummingbird beats its wings in 60 seconds. So you can see from the table, in 2 seconds it's 160 times, in 7 seconds it's 560, in 10 seconds is 800. So what we can do then, before we look at this, an example of a proportion. Again, like the book says, it's an equation with equal ratios. So for example, 1/3 equals 2/6 is an example of a proportion. So what we're going to do here, we're going to look at these ratios and see whether they're equivalent or not. So if we have 160/2, again, they did the y over the x, which again happens to be the bigger number over the smaller number. 160/2, if we reduce both of those by 2, that would be 80/1. And the second one, if we reduce those by 7, that is 80/1. And the last one, if we reduce those by 10, that is 80/1. So you can see that these are all the same. So they're all equivalent, so it's proportional. The question here, it asks us to find how many times a hummingbird would beat its wings in 60 seconds. So once we've got that proportion, or that those ratios are equivalent, I should say, we can set up a proportion. So we've got 80 times 80 wing beats in 1 second. And we're trying to find the number of times in 60 seconds. So you could on this one just say, to get from 1 to 60, that would be multiplying by 60. So 80 times 60 is 4,800. So 4,800 times the hummingbird beats its wings in 60 seconds, or in 1 minute, then we could say. One other way we could have done this, once we found this out that these were all equivalent, we could have just looked at it. Another option would have been saying from 10 seconds, if you just multiply that by 6, then that would give you 60 seconds, and it would be 4,800 times. So there might be different ways that you can work this out and still get the same answer. So one thing, as you do these proportions, as you try to solve these, one way you can do these is to try to look for a pattern, multiplying or dividing, going towards the variable. The pattern does have to be multiplying or dividing, but we can actually go either across, or we can go up and down. But again, try to go towards the variable with your pattern, because then when you're actually finding the variable, that will tell you what you need to do to find what the answer is for the variable. So this gives you a little bit of an idea about proportional relationships, equivalent ratios, and proportions, and we'll finish this up in another video. Have a good day.